Okay, so it's a real pleasure to have Ryan McKenna from UMass Amherst speaking to us about marginal-based methods for differentially private synthetic data, which should be very interesting. Thank you.
Yeah, thanks, Thomas, for the invitation to speak at this seminar, and thank you, everybody, for attending this talk. So as you mentioned, I'll be presenting and talking about marginal-based methods for differentially private synthetic data. This talk doesn't correspond to any single publication by myself or anybody else. It's just sort of my chance to sort of tell you what I've learned about this problem over the past few years since I started thinking about it fairly carefully. So I originally became interested in this problem of differentially private synthetic data back in 2018 when the National Institute of Standards and Technology hosted and organized the synthetic data competition. And so this was the first major competition in differential privacy. And the goal of this was to essentially advance the frontier of differentially private mechanisms for this important task and encourage researchers, practitioners, and programming enthusiasts to generate new ideas and mechanisms that work well in practice. So there have so far been two competitions, one in 2018 and a follow-up in 2020. In the 2018 competition, there were 20 teams that submitted at least one solution, and there was $150,000 in prizes throughout the different, dispersed to the winning teams in the competition. So the competition was split into two phases. In the first phase, we had 1 month to design our mechanisms, and we were given access to a provisional data set, which we could use to test and debug our mechanisms, as well as a provisional leaderboard where we could compare how well our mechanisms were doing in comparison with the competitors on the provisional data set. After the 1 month competition phase, we submitted our source code and a proof of privacy to the contest organizers, who had experts verify the privacy proof and implementation to make sure there were no intentional or unintentional bugs or mistakes in the privacy proof. And then they ran our mechanism on a new data set to ensure it didn't overfit to the provisional data set, and then used the performance on the new data set to determine the final leaderboard. So the competition there were two competitions, 2018 and 2020, and in each competition there were 3 sprints, which correspond to these like 1 month design phases. In one of the sprints, the data set differed between competitions and between sprints, but in one of the cases, the data set corresponded to 1940 census data. So this data set contained basic demographic information about individuals, like their age, their sex, their income, and their education. In total, there were 98 attributes in about 661,000 individuals, and the data had been pre-processed so that every cell of this table was an integer in the range 0 through A max. And the value for A max was provided to us in a separate domain file for every column. So we know that every column has a finite number of possible values, and we know exactly what the set of possible values are. So in the provisional data set corresponded to data for one state, in this case Colorado, and the final data set had the same schema, but was for 2 different data set for 2 different states, Arizona and Vermont, although we didn't know that at the time. However, for the purpose of this talk, I just kind of wanted to show you sort of what the data looked like. It's pretty high dimensional. Maybe there's a good amount of it, but importantly, the data is discrete. So every column, every attribute can only assume a finite number of possible values, and that's going to be important for the methods that I'm discussing. So if you have numerical data, then that has to be appropriately discretized before you can use any of these methods. So that's all I want to talk about in terms of the competition. Now I want to talk about sort of things that we've learned from the competition, as well as sort of mechanisms that have come out of it.
Ryan, can I interrupt for a quick question?
Yeah.
So did you know ahead of time that the data set that was going to be used for evaluation was going to have the same types of columns, same discrete data, same range?
Yeah, so we knew that the column names were the same. I believe the set of possible values could have been different. So they gave us a separate file where we were able to load in what the possible values were. But some of the columns might have had the same exact domains, like sex was always either 1 or 2. Um, but some of the columns, like city, like when you go from Colorado to um, Vermont, the set of possible cities will have different codes. Um, so
Thank you. Yeah, thanks.
yeah, that's a good question. Um, so in the competition, many of the best performing mechanisms are what I like to call marginal-based mechanisms. So the basic recipe for a marginal-based mechanism is shown here, and they basically consist of 3 steps: a select step, a measure step, and a generate step. In the select step, we first identify a set of marginal queries which we want to measure. In the second step, we actually measure those marginals privately by using some noise addition mechanism, like the Gaussian mechanism. And then the third step, we try to generate synthetic data that explains the noisy marginals well. So this basic 3-step procedure underlies marginal-based mechanisms, and it's pretty simple and straightforward, but also very general and pretty powerful as well. So there's many different ways in which you can approach each of these 3 different subproblems, and different approaches to these subproblems give rise to different mechanisms. So it's important to have good solutions to each individual subproblem as well, because if you do something suboptimal in any individual step, then you're sort of giving away some utility for free. So getting started with the measure step, that's all about identifying the right noise distribution to use and how to calibrate noise. And for that, we want to use, the latest state-of-the-art techniques like concentrated DP or Gaussian DP to make sure that we're really calibrating noise as tightly as we can. For the generate step, even if we measure the perfect marginals and we add very little noise to them, if we don't have a method that can extract utility from those noisy marginals and estimate synthetic data that sort of captures that utility, then it doesn't matter how little noise we added or which marginals we selected in the first place. And thirdly, for the select subproblem, even if we have perfect solutions to the other 2 problems, if we're naive and we select only like one-way marginals, it doesn't matter how good our solutions to the other problems are. We're never going to be able to preserve correlations between attributes or anything more interesting. So it's important to have good solutions to all 3 subproblems. The focus of this talk will be on the first subproblem, the select subproblem, where we have to figure out what marginals are worth measuring about the data. If you attended my job talk a couple of weeks ago, you will have learned a few techniques for the generate subproblem. And I may give some high-level ideas about how some different approaches for that here, but I'm not going to go into any technical depth on that problem here. So first, I want to answer the question of why do we want to measure marginals and what is a marginal? So a marginal is just a histogram over a subset of attributes, and the age by education marginal is shown on this slide. It's essentially a count of the number of records in the data set that have a given age education combination for every possible age education pair. So it can be visualized as a 2D histogram, and these are appealing statistics to measure for several reasons. First, marginals capture low-dimensional structure that's common in real-world high-dimensional data distributions. And second, each entry of a marginal is a count, and an individual can only contribute to one entry of a marginal. So that means that the sensitivity of the entire vector of counts is small, and all cells can be measured simultaneously with very little noise while protecting privacy. So this is a statistic that's highly compatible with differential privacy. However, we want to be careful about which marginals we select. So in the next few slides, I'm going to walk you through a few different methods we can use to identify marginals to select. So the first method is called the independent baseline, which just selects all one-way marginals. So essentially, it computes a noisy histogram for each individual attribute one at a time. This is a simple baseline, and it's actually pretty effective, especially in low epsilon regimes. Moreover, we can very efficiently generate synthetic data by simply sampling from each one-way marginal independently, hence the name independent baseline. And interestingly, variants of this mechanism have seen some level of success in the NIST competitions, achieving a 4th place finish in both the 2018 and the 2020 competition. In particular, it even outperformed some more sophisticated mechanisms that were based on GANs. The main drawback of this approach is that the synthetic data, because we're only selecting one-way marginals, the synthetic data will never be able to capture correlations between attributes. So it will not know that age and education might be highly correlated. So to overcome this problem, we can use something like PrivBayes, which works by selecting some carefully chosen set of low-dimensional marginals, like 1, 2, and 3-way marginals. And this allows the mechanism to capture some level of correlation between different attributes, and it's going to work much better than the independent baseline. And we can efficiently generate synthetic data by constructing a Bayesian network and fitting the parameters of the Bayesian network from the noisy marginals, and then sampling records from it. So an example structure of this Bayesian network is shown here. Each node in the graph corresponds to an attribute in the data set. And then there's directed edges between attributes if there's a dependency between those attributes. So we see that income might depend on sex, for instance. And for each node in this graph, there's a corresponding low-dimensional marginal, which we're selecting. So we're selecting the marginal on sex, the income by sex marginal, and the age, income, education marginal, and so on and so forth. And PrivBayes does provide a way to automatically determine the structure of this model automatically from the data using a differentially private mechanism. And I'm not going to talk about that, but I will talk about something related as well on the next slide. So another algorithm similar to PrivBayes is called MST, which is short for maximum spanning tree. And similar to PrivBayes, it tries to construct a graphical model, although instead of using a Bayesian network, we're instead using a Markov random field. So here, each node is an attribute in the data set, and each edge corresponds to a 2-way marginal which we're selecting. So in this case, we're selecting the income by age marginal, the income by sex marginal, the income by city marginal, and the age by education marginal. So once we have these marginals, we can fit the parameters of the Markov random field using a technique called private PGM. And then once we have the Markov random field parameters, we can use it to sample and generate synthetic records. So this mechanism was used in both variants of this mechanism were used in both 2018 and 2020 and came in 1st and 2nd place respectively. The main drawback of this approach is that it restricts attention to only 2-way marginals, so it's not going to be able to capture higher order effects. Now I want to give a little bit more details on how MST selects 2-way marginals. So basically it's an iterative algorithm for selecting marginals, and it can be seen as a differentially private implementation of the Chow-Liu algorithm, if you're familiar with structure learning in graphical models. But basically the idea is we're going to initialize P0 to be a model that assumes independence between attributes, and it's obtained after measuring all one-way marginals with some fraction of the privacy budget. Then we're going to initialize an empty graph T, and for every pair of attributes that are not connected in T, we're going to compute the L1 distance between the true 2-way marginal and the estimated 2-way marginal under the independence assumption. And then we're going to invoke the exponential mechanism to select a candidate with nearly maximal score. We repeat this procedure until T is a connected graph, in which case it is a tree. And the intuition behind this quality score is that candidate marginals, which are already estimated well under the independent model, will have lower scores, meaning that they don't have to be selected. So this algorithm can be seen as a differentially private implementation of Kruskal's algorithm, for computing a maximum spanning tree of a weighted graph, where we simply replaced the step that selects the sort of highest weighted edge with a call to the exponential mechanism. And the reasoning for restricting to a tree structure is purely computational. So it turns out that fitting and sampling from the Markov random field is most efficient for tree structured models. So by restricting attention to trees, we were able to run on the high dimensional settings which we encountered in the competition. So that's MST. There's a few differences between PrivBase and MST. One that I think is important to tease apart is the choice of the model structure. So PrivBase utilizes a Bayesian network, while MST uses a Markov random field. So for a Bayesian network, the graph has to have a very specific structure. It has to be directed and acyclic, and that means that you can only measure one marginal per attribute. In contrast, for the Markov random field, the graph is undirected and can have cycles, and essentially it can capture any subset of marginals, including higher order marginals, not just two-way marginals. Additionally, another distinguishing feature of Markov random fields is the way that the parameters are estimated. For the Bayesian network, the parameters are estimated using a local heuristic that truncates noisy counts to 0 and then normalizes to obtain conditional probability tables. In contrast, with the Markov random field, we're using private PGM, which estimates the parameters by solving an L2 minimization problem. And it combines all information about the noisy marginals rather than just local information about the one marginal we're estimating. So because Markov random fields are more general than Bayesian networks, you can actually take the marginals selected and measured by PrivBase and pass them into private PGM to estimate a Markov random field. And if you do this, you get a new mechanism called PrivBase plus PGM. And this new mechanism consistently performs better than PrivBase by itself. So in this plot, we've run these two variants of PrivBase on 4 data sets, and we're measuring their workload error, where lower is better. And we see that on all 4 data sets, PrivBase plus PGM achieved lower error than PrivBase, and in some cases, the error was up to a factor of 6. So so far, I've introduced 3 mechanisms: the independent baseline, PrivBase, and MST. Now, these mechanisms are nice, but they're missing, in my opinion, one important ingredient, and that is the notion of a workload. So workload is just a set of queries, statistics, or other aggregations that we want to preserve in the data. And workload-aware mechanisms are specifically designed to offer low error on the workload. These are appealing when we know what the synthetic data will be used for up front, because we can tailor the synthetic data for the queries in the workload. However, PrivBase and MST are workload agnostic, so they totally ignore the workload, they have no idea what it is, and they select marginals based only on the data. So, in my opinion, I think we need mechanisms that can generate synthetic data that are tailored to a workload. And there are some available already today that I'm going to talk about. But for the purpose of this talk, well, a workload in general is an abstract object that can represent many different types of analyses that you might want to do on the data. But for simplicity in this talk, we're just going to assume that a workload is a subset of marginal queries. And the notion of a workload is something that PrivBase and MST are lacking. So how can we design mechanisms that are tailored to a workload? What marginals should we select is the question. A natural idea is to select the marginal queries that are in the workload. And for small workloads, this is in some sense the right thing to do, because the selected queries are exactly what we care about preserving. And so we're spending our privacy budget on exactly that. However, for large workloads, the main problem with this approach is that the amount of noise that we have to add to each individual marginal depends on the number of marginals that we're measuring. So for very large workloads, it may be an inefficient use of the privacy budget to try to measure every marginal query in the workload. So a natural idea for large workloads is to select a small subset of the workloads. And in particular, we can focus on selecting the marginal queries in the workload that are most important. And if we do this carefully, then we can both preserve the selected marginals and the non-selected marginals well. So that's the basic idea. And the mechanism that sort of does this is called MWEM plus PGM. So this is an algorithm that combines the popular MWEM algorithm for linear query answering under differential privacy with private PGM, which enables it to scale to high-dimensional settings. So the algorithm is an iterative algorithm, and it begins by initialing P0 to be an initially uniform model. And then it proceeds for a number of rounds, and in each round it does three things. In the first step, it selects a marginal query from the workload that is poorly approximated under the current model, which it achieves using the exponential mechanism. Then it measures the selected marginal privately using the Gaussian mechanism. And then it updates the models by fitting it to the noisy measurements made so far using private PGM. So like before, the quality score function that we're using for selection is just the L1 distance between the true marginal and the estimated marginal under the current model. So intuitively, what's happening is this algorithm is trying to adaptively identify which marginal it is doing poorly on and fix itself by measuring that marginal and incorporating it into the model. So this mechanism differs from the original MWEM algorithm by replacing the multiplicative weights update step with a call to private PGM, which instead fits a Markov random field to the noisy marginals. So unlike the original MWEM algorithm, PT is not represented explicitly, but rather implicitly as a Markov random field. And this is what allows this algorithm to scale to higher dimensional settings than it was previously possible. Now, MWEM plus PGM is not the only scalable instantiation of the MWEM algorithm. There are other algorithms which are similar and overcome the scalability limitations. So for example, the PMW pub mechanism is able to scale by utilizing public data, and in particular by assuming that PT is only supported over the domain of the public data. Then you have methods like RAP, which scale by replacing private PGM with a call to a relaxed projection step that can essentially be seen as fitting a mixture of products as PT. And then you have GEM, which is similar, and it scales by parameterizing PT through a neural network. So these are all different scalable implementations of the MWEM algorithm, but as I mentioned in this talk, I'm focusing on the select problem. So which method you use here, there are a lot of interesting things to discuss about the pros and cons of each method, but that's going to be out of scope for this talk. So the main drawback of, so M1PGM is a nice algorithm, but the main drawback of it is that it can have inconsistent and unpredictable scalability, since the complexity of the model learned by private PGM depends on which marginal queries were selected in each round. So in the best case, it will be able to run efficiently for many, many rounds, but in the worst case, if it selects the wrong marginal queries, the complexity of the model may blow up very quickly and it could fail to scale after a few rounds, a handful of rounds. So this is undesirable because we want mechanisms that are able to consistently scale no matter what dataset or workload is fed as input. Luckily, this problem is not that hard to solve, and we can make one simple modification to enable this mechanism to scale. To talk about that, I want to discuss PrivMRF, which is a new mechanism, and it looks very similar to MWEM plus PGM. PrivMRF was published a few months ago at VLDB, and on this slide I'm showing the pseudocode for this mechanism, for one component of this mechanism, I guess you could say. And note that this mechanism is not workload aware, so it determines the candidate marginals automatically from the data rather than from the workload. But other than that, the algorithm is exactly the same as MWEM plus PGM, almost exactly the same. But the reason why this mechanism is able to scale is because the set of candidate marginals is chosen carefully so that no matter which marginal queries are selected from it, the underlying model estimated by private PGM will always remain tractable. So this ensures that the mechanism will always have a consistent runtime. Now, PrivMRF is a very nice mechanism, and this semester, the past few months, I've been thinking a little bit more and running some empirical tests to sort of evaluate many of the mechanisms that I've talked about. And one interesting empirical finding I've made is that even though PrivMRF is a workload agnostic mechanism, it actually outperforms all existing workload-aware mechanisms, even when they're evaluated on the workload that they're optimized for. So in this plot, I'm varying the privacy budget on the x-axis, and I'm measuring workload error on the y-axis, where lower is better. And each line in this plot corresponds to a different mechanism. So the orange line corresponds to the PrivMRF mechanism, while the purple, brown, and pink lines correspond to workload-aware mechanisms. And what's interesting is that PrivMRF sort of matches MST, the performance of MST in the low epsilon regime, and it's better than every other mechanism in the high epsilon regime. And in all epsilons, it's always better than the best workload-aware mechanism. So this is a pretty remarkable thing, a remarkable property of PrivMRF. It's really doing a good thing, and it's not unique to this data set or workload. I've also tested on 6 data sets and 3 workloads, and it really is consistently better than all the competitors in almost every case, except for sometimes in the very, very low epsilon regime. 2 of the data sets are shown here. But what this suggests is that there's a need for more work in this space, because we know that workload-aware mechanisms have an inherent advantage. And we know that workload agnostic mechanisms like PrivMRF that try to provide accuracy on all possible workloads are necessarily suboptimal on the workloads actually used to evaluate them. So we should be able to beat it, but it is the current state of the art. So in the remainder of the talk, I want to discuss, if you're doing research in this space, what the types of considerations you should have in mind when you're trying to decide how to design new mechanisms, and in particular, how to select marginals to measure. So I've identified, so basically, we want to be careful about the number of marginals that we measure, because as we measure more marginals, we also have to add more noise. So there's a delicate trade-off between how many marginals we select and how much noise we have to add. I've identified 4 criteria which we can use to evaluate different marginal selection procedures. And these are criteria that we want these procedures to have. So these are budget awareness, workload awareness, data awareness, and efficiency awareness. And on the next few slides, I'm going to talk a little bit more about each of these individual criteria. So a budget-aware mechanism is a mechanism that adaptively selects marginals based on the privacy budget available. So the basic idea is that when your privacy budget is low, you probably want to select fewer and lower dimensional marginals. But when your privacy budget is high, you can afford to measure more higher dimensional marginals. So we want a mechanism that is budget aware, and it sort of adaptively figures out what regime it's in and selects the appropriate number and right kind of marginals. So when we compare a budget aware mechanism to the baselines, like the workload baseline and the independent baseline, at low epsilon regimes, we want it to be comparable to or better than the independent baseline, because that's sort of like, it's kind of hard to beat that. And in the high epsilon regime, we want the mechanism to eventually get down to 0 error, like the workload baseline does. The second consideration for selection is we want workload awareness. So we want to select marginals based on what the workload is. We don't want to be wasting our privacy budget measuring marginals that are not relevant to our evaluation criteria. And so we'd expect that a workload-aware mechanism, when evaluated on the workload, should be able to deliver lower error than a general-purpose mechanism. this might come at a cost of higher error on things that are outside the workload. The third criteria is data awareness. So we want to select marginals. We want to be able to adaptively select marginals based on the characteristics of our data. So for instance, if we have a data set where two attributes are approximately statistically independent, we don't want to waste our privacy budget to measure that two-way marginal if we can estimate it well just by measuring their one-way marginals. So when you compare a data-aware mechanism to a data agnostic mechanism, like the workload baseline, the workload baseline should deliver similar error on almost all data sets. Whereas a data-aware mechanism will be able to exploit structure in data sets that have structure and should be able to deliver much lower error on those cases. The final criteria, which we can use to evaluate a selection procedure, is efficiency awareness. So we want to select marginals so that we can consistently scale to high dimensional data sets in large workloads, and we want to select these so that whatever post-processing method we're using to generate synthetic data will be tractable and efficient. So we want to sort of avoid the failure mode of M1 plus PGM if we can. So those are the four criteria, and we can evaluate the prior work along these four criteria. So beginning with the baseline mechanisms, the independent baseline is extremely efficient, but it's not budget, workload, or data aware because it always selects the same marginals no matter what these things are. On the other hand, the workload baseline is workload aware because it measures different things for different workloads, but it doesn't try to change what it measures based on the budget available or based on the characteristics of the data. And moreover, there's some question marks about how to efficiently generate synthetic data after measuring all the marginals in the workload. And so it's also not an efficiency aware mechanism. Then you can go to mechanisms like PrivBase, MST, and PrivMRF. These mechanisms satisfy a lot more checkboxes than the other ones, but none of them are workload aware, so they're missing that important ingredient. And then when you look at the MWEM variants like MWEM plus PGM, WRAP, and GEM, they're workload aware and data aware, but then they're not budget aware because they always run for the same number of rounds. Technically, the number of rounds is a hyperparameter, but there's not really much principled guidance on how to set that hyperparameter. We know intuitively that if you have less budget, you probably want to run for fewer rounds. If you have more budget, you might want to run for more rounds. But none of these methods really discuss how to set that hyperparameter based on the budget. So it's clear that there's no mechanism that satisfies all four checkboxes, but in the next remaining few slides, I want to talk about how we can revisit the M1 plus PGM algorithm and make a few simple modifications to improve the mechanism and make it budget aware, efficiency aware, and also make some other improvements. So on this slide, I'm showing the M1 plus PGM algorithm again. Now I'm going to make a few incremental changes, which each one is very small, but together they make this algorithm significantly better. So the first change is to replace this initial model, which was originally a uniform model, with an independent model obtained from noisy one-way marginals. So this means we spend a small amount of the privacy budget to measure one-way marginals, and then use those one-way marginals to construct this independent model. This is essentially a way of warm starting MWEM, and it allows it to make faster progress. So that's the first change. The second change is going to make it efficiency aware. So rather than selecting a candidate from the workload, we're going to filter out candidates that would make the model size intractably large if it was selected. So we're going to only select candidate marginals that we know will keep the model sufficiently small. This will ensure that the resulting mechanism will always be able to scale no matter what data set or workload is input, or however, no matter what is selected in each round. So that makes it efficiency aware. The next modification we're going to make is changing the quality score function for selection. So now it's a difference between two terms. The first term is the error on the marginal under the current model. And the second term is the expected error on the marginal if we measure it with the current noise scale. So this is equal to the square root of 2 over pi times the standard deviation of the noise times the number of cells in the marginal. So this modification actually makes this mechanism budget aware, because if you look at, so I guess, sorry, let me back up. This quality score function essentially captures an expected improvement in error if we measure something, rather than just the expected error of the thing on the current model. And so this modification makes the mechanism budget aware, because if you look at this term, here, it has a sigma and it has an NR. So what this means is that when the privacy budget is low, sigma will be high. And the mechanism will not try to select marginals that have large values of n, because that would severely penalize the score. In contrast, if the privacy budget is high, then sigma goes to 0, and we can afford to measure larger marginals. So this makes the mechanism, in some sense, budget aware. The next modification we can make is to replace the set of, is twofold. So first, we're going to replace the set of candidates. Instead of only selecting marginals that are in the workload, we're going to consider marginals that are in the downward closure of the workload. That's what W plus is. So that means any marginal that's a subset of one of the marginals in the workload will be considered as a candidate. This can be useful because if you have a workload with like 5-way marginals, maybe every single marginal in the workload has too many cells to really get a good signal to noise ratio. And it may be better to instead measure lower order marginals and then try to construct the higher order marginals from them. So we're changing the candidate set to include the downward closure. This means we're going to be able to select lower order marginals that aren't in the workload. And we're also including a new term, a W of R, which essentially weights the importance of a candidate based on how relevant it is to the workload. The final change that we can make is getting rid of the pesky hyperparameter. So instead of running for a fixed number of rounds, we can just run until we use up all of our privacy budget. And we're going to adaptively reduce the noise standard deviation as we proceed through the mechanism. So if we get to a round where we don't learn much in that round, like if the difference between PT and PT minus 1 is small, then we're going to reduce sigma because we've sort of stopped learning much at the current value of sigma. So this means the mechanism will run for a different number of rounds. And what happens in practice is that when the privacy budget is small, sigma will be reduced very quickly because we're not learning very much very quickly. Then when the privacy budget is large, we're going to run for a large number of rounds before we attempt to reduce sigma. So this makes the mechanism even more budget aware than it already was. So each of these modifications is very simple, but when you combine them all together, you actually get a state-of-the-art mechanism. So going back to the plots we saw before, I've removed all the other mechanisms which were not beating PrivMRF, and I'm just comparing this new mechanism, which we're calling AIM, with PrivMRF on one workload. And we see that it's consistently better than PrivMRF on all data sets, and the magnitude of the improvement is substantial in some cases. So simplicity can be effective. I guess another thing that is interesting to look at is that the metric that we're using to evaluate error is workload error, but workload error can be a little bit tricky to interpret because we know lower is better, but we don't really know how low is good. Like, we might need to know this if we want to figure out what to set the privacy budget to. So for this, we can come up with a more interpretable way to present the performance of the mechanism by comparing it with a non-private mechanism that samples K records with replacement from the data set. So what we're showing here is for a given error rate, we can calculate the number of samples needed for this subsampling mechanism to achieve that error rate, and then plot that as a function of epsilon. So looking at this plot here, we see at epsilon equals 10, that roughly correspond for the AIM mechanism, that roughly corresponds to a sampling rate of 100%. So that can be used to say that, okay, maybe at this privacy level, we're not losing much utility in our data compared to it, or we can at least say that compared to this baseline of sampling all of your records with replacement, it's comparable. So that might be an acceptable cost and utility for analysts. And it could be a useful way to communicate error. But this is about it that I want us to talk about. So in this talk, well, in recent years, there's been many mechanisms available for private synthetic data. And but I still think that there's a lot of work that needs to be done in this space. And I think with a few simple improvements to M1 plus PGM, we can make a state-of-the-art mechanism. But there's still a lot of open problems to consider and probably more improvements over what I've shown you here. But some problems that I think are important are being able to handle mixed data types effectively. So in this talk, we assume that the data was discrete. And while there are some techniques that can handle mixed data types, I don't think they outperform the marginal-based mechanisms that I've talked about here. So that's something that's important. Another thing that's important is being able to quantify and communicate uncertainty in the synthetic data. So if someone's doing some analysis on the synthetic data, we need to tell them, should you trust this result or should you not trust this result? How much error do we think there might be? And being able to communicate that is pretty important in practical deployments. And finally, I think incorporating public data is something that's underexplored and needs more attention. There has been some nice preliminary work on this topic, but I think there's a lot more to do there and a lot of different ways in which public data can come into the picture. So that's all I wanted to talk about, and